critical, critical exponent values. So if it is something like 1 over root 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4, is that convergent or divergent?
Convergent.
Huh? That's divergent. That's divergent. This is divergent. And how about 1 over 2 square, 1 square, 2 square, 1 over 3 square, 1 over 4 square, 1 over 5 square? This one is convergent. This we learned last time using the integral test. And I said the integral test mostly is helping us to deal with P series. You can use the integral test for other stuff, other series, but usually when you're able to do that, you probably will be able to deal with other means anyway. And so the main achievement of the integral test is to establish facts about P series, because we know very well how to deal with a function, 1 over x to the p, because we know how to take antiderivative and all that. So therefore, we result the integral test to help us understand the P series. Okay, now you see that guy is divergent, that guy is divergent, and this guy is convergent, right? Okay, now comes this. Let me ask you then this question. I take that bad guy, the first one, then I'm going to alternate it. I'm going to be alternating it, which means that I switch back and forth between positive and negative. This is convergent or divergent?
No idea.
No idea. Okay, now in silence, I'm going to prove that it's convergent. Right? You bring out the most important aspect of the formal proof. So, how do you represent a series, a sequence? A sequence, one way of doing it is do that, x, y thing, and then this dot, right? Just think of a sequence as a function with domain in n instead of natural numbers. But when it comes to series, you can't do that, right? Okay, so kind of series, you can think of it as the sum of rectangles, and we do last time. It's kind of awkward. All right, so this one I'm gonna create something. Okay. So here is a real number line, and I'm summing, correct? And I'm summing sine numbers. Unlike that one, as I throw in more and more terms, each extra term will give a positive contribution. All right? And therefore the partial sum is keep pushing to the right. But this one is different. You start with 0. First partial sum is what? 1. All right? That's 1. So you think of this as this. Start from nothing, throw in the first term, then you go to the right. Now I'm at 1. What's the next move? You throw in a negative term, right? Negative term. So you go to the left. To the left. So now you go to the left. So now you're somewhere between 0 and 1. Right? What's the next step? Third term. To the right. To the right. Somewhere. So in next term, what happened? To the left. How long? Not as long as this one. Is that right? See the picture? Okay. Now, then I am going to focus on partial sum of the first two terms. Where is it? It's over here, or more precisely, oops, wrong color. It's over here. No, projected down is down here, is that right? So that's where what? S2 is, right? S2 means what? The sum of the first two terms. The first term is positive, second term is negative. How about S4? So from S2, you throw in two more terms, right? So therefore, you have two zigzag. And that brings you where? Here. What is that? S4. Right? Are you, compared with S2, are you convinced that you're sliding to the right? So you have this zigzag thing, but you know this the amplitude of oscillation gets smaller, and that's the point. And therefore, you start with 0, then you go this, and as you return, you do not return to that place, right? And then you turn again, and each time you do not move as much, and so you keep. If you look at these points where you stop and turn to the right, those turning places get pushed to the right. Are you with me? But then on the right, you have these turning points as well, right? So if you look at those, what is S1? S1 is exactly here, right? So that's S1. And then where is S3? Here. That's S3. Yeah? Get the picture now? So what do you notice? If you look at S2, S4, S6, you know, the left end of the oscillations, then because the amplitude oscillation keeps shrinking, right, every step of the way, and therefore those turning points get pushed to the right. So if you look at just S2, S4, S6, they themselves form a sequence. And that sequence is increasing sequence. Is it bounded above? Yeah? And so we have that abstract theorem, which says that if you have an increasing sequence which is bounded above, it better be what? Convergent. Likewise, if you look at S1, S3, S4, you know, you have another sequence, you know, coming from the left. Isn't that decreasing sequence? All right? And then isn't it a decreasing sequence bounded from below? And therefore, it also is guaranteed theoretically to have a limit. And would you agree that these series gets closer and closer? So it looks like they are approaching the same number then. And that same number must be the limits of Sn. Right? Okay, so that's essentially what it is. Okay, if you look at the proof in the book, it's slightly more careful. It essentially says that what it does is that why don't we look at S2 first, S4, S6. Just look at the left-hand side. Then it's the increasing sequence bounded from above, and therefore it has a limit, right? And how about the other guy, S3, S1, S3, S5, and so on? And you just notice that, well, S5, for example, is S4 plus what? A5. Is that right? So in general, S of 2n plus 1 is equal to S2n plus A5. 2n plus 1. So if n goes to infinity, if this one stabilizes, and if this one goes to 0, which it is in our case, and it goes to 0, and therefore this sum has a limit, the same limit as the limit of S2n. And that more exactly proves that this one indeed. But what I'm showing here is that you should keep this geometric picture in mind. Essentially, it's oscillating with a progressively smaller amplitude. Every step of the way, and that's exactly.
Kind of flatline at one point? Does it just kind of like flatline at one point?
And it's like it's essentially like if you look
like
at
a
the
sine
partial
wave?
sum, if you look at the partial sum, as a sequence, right? Partial sum itself is so S S1, S2, S3, S4, like this.
So is it like a sine wave that's getting
Yeah,
compressed?
yeah, exactly. So it's sort of stabilized. So you have a certain height, 1, right? From nothing, and then S1, and then S2, S3, S4, S5. It's keep oscillating, and it's stabilizing to a certain height. Okay, so that's what it is. But this doesn't tell you what that sum is. Once again, this is yet another case, where we just we just draw a conclusion as to whether it converges or not, but this doesn't tell us sum. So here comes the thing here is that you have the key point is that each step, these steps keep getting smaller and smaller, and then its direction keep alternating. So these two features. It's alternating, and secondly, the step size gets smaller and smaller. So how do I polish up and make a statement? The statement is this. So statement is that here. And this theorem has to do with alternating series, and this is alternating. This is alternating series tests. So this is what it is called, alternating series test. These are by no means a standard terminology, So after a while, just forget about what that name is. Just know how to do it. If you look at some other book, perhaps they're called something different. Anyway, so what's the essence of things here in that first example, first alternating series? You see that if an alternating series, so first I have to define officially what is an alternating series. Okay, so that's alternating series means a series whose the sign of whose terms keep alternating from one term to the next. So if you start with, doesn't matter whether you start with positive or negative, right? It's positive, negative, positive, negative, positive, negative. That's what alternating series means. And then you need to capture two things. So a general form of alternating series is like this. So if you're interested in this one, alternating series can be written in this way. Well, let me use G.